Oops. So up to this point, all of our bonding involved what is called end-to-end overlap. In end-to-end overlap, I could have an S overlapping with another S. I could have an S overlapping with a P. Or I could have two p orbitals overlapping as long as it was on the ends of their p orbitals. We called these bonds sigma bonds. And I described it like holding hands. There's only one region of overlap when you're dealing with a sigma bond. They're the simplest. Another important feature of a sigma bond that I mentioned yesterday is that you can actually rotate molecules around that sigma bond. You can rotate around them. What I want to talk about now is what happens when we have a double bond formed. When a double bond is formed, it is due to the overlap of two sp2 orbitals to form a sigma bond. So we can still have overlap of those hybridized orbitals with a p or with an s as long as it's end-to-end. And in a double bond, that same thing happens. So a double bond is actually made up of, firstly, a sigma bond, a good old regular end-to-end overlap. And secondly, the second part of the double bond is something that happens when we have two non-hybridized orbitals to form what we call a pi bond, non-hybridized p orbitals. The term pi originates same place where the term sigma came from. Because we thought of it as two s orbitals coming together, the simplest form is the Greek letter for s, sigma. When we have two p orbitals overlapping in this special way, we call them pi orbitals, which is the Greek letter for p. Now we've already seen p orbitals overlap end to end, but this bond is different. We're going to have the p orbitals overlap in a sideways fashion, all right? Little definition of what a pi bond is. I actually have a bullet that I should add to it, and I'll just write it in. When it comes to determining the type of hybridization and ultimately the shape, pi bonds are not counted as lone pairs or bonding pairs. We simply ignore them. We could say that they have no effect on the shape, but they kind of do. They affect that shape that we've already determined for the various types of hybridization. They affect the fact that this is going to be a linear situation and that this is going to be a triangular planar situation. So some textbooks will say they have no effect on the shape. We ignore them when determining the shape. In the end, they do ultimately have that effect, but because of the way we've defined things here in terms of their shape, we're really kind of ignoring them. So I'm going to go along with what many textbooks will say. The pi bonds are not counted as lone pairs or bond pairs. They do not affect the hybridization or shape. I'm going to put hybridization slash shape. The hybridization determines the shape, right? So we're really saying the same thing. So when we have a double bond in our Lewis diagram, we actually don't even count it in order to determine the hybridization, all right? When we start drawing the orbital view, we will have to count it, and we'll start to see how that shape comes out of it. Okay, so now let's just do some examples, and I'm going to switch back to the Smart Notebook. I just have to check what the example is. So H2CCH2, and that's what the example is going to be. And I'm going to follow along the exact same set of things that I've been doing all the way along. So the example, what was it? H2CCH2. And we're now under examples concerning double bonds. So as you can imagine, we're going to have a double bond in this. And I'm hoping you can come up with the Lewis diagram for this. I hope. Again, we're following all of our good rules that we learned in grade 9 and 10. All the carbons have to have 4 lines. All the hydrogens can only have 1 line. This isn't what I would call an ugly structure. It doesn't have any, deviations from the octet rule. What do we have for a picture here? Somebody going to tell me? I'm actually asking. What do you got, Mallory? What do you got? Yeah, they both have an H on it. And I'm going to just draw it like this because we're really not worried about the 3D Lewis at this point yet, but we're going to get there. Okay, so now we have to go through our regular analysis that we usually do. These two carbons are exactly the same, so we can analyze them together. And in the analysis, like I said, the pi bond does not have any effect on the shape or the hybridization. So we ignore the second bond. We ignore the double bond. So as I analyze this carbon, I see a sigma bond, and this first bond is a sigma bond. The second bond in the double bond is the pi bond. So this carbon has 3 bond pairs and 0 lone pairs, because I ignore the multiple bond. And you know what? The other one has the same, so I'm not even going to write it out. I'll just put the arrow that goes along with that. It's got the same. And so we can use what we've learned in the past. I have 3 in total, whether it be bond or lone pairs. And therefore, what type of hybridization is it going to be if I need 3 identical bonds? What's it going to be? Yep. sp2. So it's sp2 hybridized. sp2. So what's the electron pair arrangement? I'm just thinking ahead to my 3D Lewis. How are those 3 electron pairs going to be distributed in 3-dimensional space? What's the shape called? Yep. Trigonal planar. I think that's the only one I didn't even write down there. Excellent. Trigonal planar. So the EPA is trig plan. So already in 3-dimensional shape, we're starting to think about what it looks like. Let's do the energy level diagram. I'm going to need 2 sp2 hybridized carbons. Carbon, oh, let's change to black. Carbon, helium. sp2 means I use 2 of them up. And then I have, wait a minute, I need 3. I use 3 of the 4 up, and I've got 1 lone P. 1, 2, 3. There's the S and the P2, sp2, and I've got 1 lone P. And I still have 4 electrons. 1, 2, 3, 4. And I'm going to have another one right below it, exactly the same. And I'm getting this information from here, right? This information here, this 3, tells me the sp2, which tells me this. 1, 2, 3, sp2, 1, 2, 3, 4 electrons in it. And before I even worry about the hydrogens, let's make the bonds. As I just defined, in a double bond, the first bond is a sigma bond between 2 sp2 orbitals. The second bond, which is the pi bond, the second bond of the double bond, exists between the 2 unhybridized p orbitals. And that's a pi bond. Now I need 2 H's sigma bonding with the rest of the orbitals here. So I'm just going to put my circles. We're going to make the boxes around it. We're going to finish the bonding. So again, in this case, I need an H. You'll notice I've kind of stopped drawing the H. If I get you to do that as a test, if you want to be lazy and not put that H in there, that's not a big deal. I know that that circle is a hydrogen, a 1s. I need another one here, another H. Down here, I need another H sigma bond. Down here, another H sigma bond. Let's take a look at the orbital view. Now, again, I could draw it on the board, but I've got my nice little shortcuts here, so let's use that. Oh, and I've got to open the gallery each time. My content, got to hit it twice. What a silly program. Oh, got to hit it twice. And I want orbitals, and yep, it won't open. Oh, yeah, I got to do that. Okay. So what do I have? I have 2 SP, where is it? Where's my SP2? Did anybody see my SP2 go by? Where'd it go? B? Oh, SP2, right there. There it is. So I've got 1 SP2, all right? And now I'm going to have a second SP2. And I have to rotate this one. Now you're not going to draw it, in terms of rotating, but I'm going to do that. And I'm going to have it overlap like this. So that's a good start for you guys. You can put the 1, 2, 3, and you might think, why don't you just put it flat on the board, Mr. Sanders? Because it's a trigonal planar. Why don't you just put it flat on the board? And the reason I'm not is because I want to show you the pi bond. Now, before I show you the pi bond, let's finish off the other bonds. Let's get the s orbitals. All right, so let me get my 1s. And I'm going to put 1 there. And I'm going to get 1. I'm going to put 1 there. And I'm going to get 1. And I'm going to put 1 there. And I'm going to get 1. And I'm going to put 1 there. So those are my hydrogen atoms kind of stuck on the side of those. And they all have their pair of electrons in there. There's their pair of electrons in the overlap pair of electrons. And they're all sigma, because they're all end-to-end overlap. And I'm going to just put sigma down here in the middle of this guy, because in a moment we're going to have a pi bond that I want you to kind of look at. Okay, so now let's deal with these p orbitals. The p orbitals orientation will be up and down in this particular perspective diagram, because I've got these 3 in the plane and the p orbitals are up and down. So I'm going to have to get from my particular picture a couple of p orbitals. And I need to put them right in there as if they're sticking up and down. Things moving too fast? Easier if I draw it on the board maybe because you can follow it. But this looks much nicer than the pictures. Yep. Yeah, you do. You're going to put those p orbitals in because this time I'm going to show you what the pi bond actually looks like. So you're right. They don't contribute to the shape. We can ignore them. but they do have significance. I want you to see this here. So let's do one more here. Let me grab that second p orbital, and I'll never get it on the right spot because it always needs some adjusting. And why did that switch to that? I think we're good. Okay, beautiful. 2 p orbitals. We're okay with the picture so far? We got it? Now, remember, in reality, the p orbitals aren't just these tiny little skinny barbells. They're actually very wide and kind of bulbous barbells. But if I were to draw them that way, our picture would be so convoluted you really wouldn't be able to see anything. But what I'm trying to say to you is that the pi bonds actually overlap so widely that they actually overlap up here and they overlap down there. The way I'm going to represent that pictorially is just with some shading indicating that they connect. So I'm hoping this works. If I pick up a pen and I think if I switch this, is it going to allow me to switch it to a different type of pen? No, that's not going to work. Let's try this. If I click on this, no, that's not going to work. I was hoping to turn this into a highlighter or maybe some kind of a crayon, then I could do some shading. On the chalkboard, I shade with the chalk. I'm going to have to just pick a different color here, and we'll go with this. And there is, see, I can't make that change. Doesn't matter. There's overlap here, and there's overlap here. And that's about as good as I can do it with what I've got here. It's not a big deal. So those p orbitals overlap in 2 positions. So that's what makes a pi bond different than a sigma bond. A sigma bond overlaps only in 1 spot, which is why it can rotate. But a pi bond can overlap. It overlaps above and below the sigma bond. Now this is 1 bond, ladies and gentlemen. This peach color here represents 1 bond. You might look at that as a new student and say, that looks like a triple bond to me. There's 3 spaces where there's overlapping, but that's what makes a pi bond different than a regular sigma bond in that there's overlap here and here, and my 2 electrons can exist up here or they can exist down here, but I'm actually going to just I'm just going to put them up here. But just like a p orbital, they can exist above and below. It's like we've made a super big p orbital. And so this thing here is the pi bond. Since I put the electrons up and down there, I'll put the pi down there. That's 1 bond. That's what makes the pi bond a little stronger than a sigma bond. There are 2 regions of overlap. It overlaps above and it overlaps below. Pi bonds restrict rotation. You can't just rotate a pi bond. What's going to happen to the overlap if you try to rotate the pi bond? Let's say you try to flip that thing through 180 degrees. Nail down 1 atom, take the other atom, the other carbon atom, and try to rotate that through 180 degrees. What's going to happen? It's going to break. You're going to have to break the overlap in order to reestablish the overlap on the bottom side. Pi bonds do not rotate freely. You can get them to rotate. You've got to hammer them with a little more energy, and it'll be like a break and then a flip and then a re-stick. But you can get it to flip because chemists have looked at things that have maybe 1 chlorine atom over here and 1 chlorine atom over here, and they can see that a little bit of energy will make a flip. It can be done, but it's not as easy as like a single bond that just that rotates and spins like a pinwheel or like a little windmill on a pinwheel type thing. Excellent. That's a pi bond. That's good stuff. Isn't that a beautiful thing? I think that's a beautiful thing right there. That molecule. It's a great thing. 3D Lewis diagram. Because we don't have to worry about drawing in the pi bond, 3D Lewis diagram, we can put everything flat on the page. So I can take this and turn it a little bit and put it flat. I can just go C, double bond C. And now that I know that I've got sp2 hybridization, what are my angles going to be between my bonds here for sp2? What are the angles? Hannah, you don't actually have to look at your notes because I've put them on the wall for you. What are the angles for sp2? Yep. 120. So I'm going H, 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 H. So to draw it as this, with those 90 degrees at this point in your chemistry career is wrong. Because you should know that if I've got 3 bond pairs, it's sp2, and sp2's shape is trigonal planar, I should draw it as trigonal planar. Okay? That's a pi bond. That's fun. That's good stuff. My next example, and I got to do a little check back here. Well, there's a representation of the pi bond on that little schematic. All right? So there they've drawn a little perspective diagram. Here we've got the end-to-end overlap for the sigma bond. The p orbitals can overlap sideways. And so they actually have it like as a space in which the electrons can be. I did it as a little bit of a shading, and there you can see the pi overlap on the top and the bottom. Excellent. Hold on one second. I'm going to change this up. Let's do a triple bond example, and then I'll do some mix-up ones for you, because that took like really long, but that's okay. I'll do a triple bond example, and then we'll shake it up. We'll do some different ones and make you think about which it's going to be. When a triple bond is formed, it is due to the overlap of 2 sp orbitals, 1 sigma bond, and 4 non-hybridized p orbitals, 2 and 2, right? So when we say 4, we mean a pair and a pair overlapping. Just like in the double bond, the first bond formed, we think of as the sigma bond. And then every subsequent bond that is made are pi bonds. Okay, so in this case, we have 1 sigma bond and 2 pi bonds. Now, when I say first, there is no temporal, there is no temporal steps involved in making the bonds. It's not that when a carbon is triply bonded to another carbon, they get together and say, okay, let's figure this out here. First, let's put together the sigma bond. It doesn't work that way. As the atoms come together, the bonds form, right? They overlap, and all the bonds are formed simultaneously. But in terms of analysis, it is a useful thing to think of the first bond put together is the sigma bond, and then we've got these subsequent pi bonds that come afterwards. In reality, they just form all at the same time. Let's do H, C, C, H. And I know this is not earth-shattering or groundbreaking in any way. You can probably imagine that we're going to deal with a triple bond between the carbons, which is okay. Again, I went through the same process last year. The things we did last year was just the Lewis, right? So we would go H, C, C, H, and you'd say, is this right? Is this right, Mr. Sanders? I say, way to go, good job. And you were excited for the fact that you understood it. That's where we got to last year. Now we can do so much more. Isn't that fun? So let's analyze now each of these carbons. In this case, each carbon is the same, so we can analyze them together. How many bond pairs? 2. We only count the sigma bonds as the bond pairs. We are not counting these multiple bonds. 2 bond pairs. How many lone pairs on this? 0. We're starting off with the easy one, 0 lone pairs. So I've got 2 bonding pairs, 2 pairs that are going to affect the shape. Therefore, the hybridization is SP. Therefore, the EPA, we're starting to think of what this thing is going to look like. What's the EPA for SP? Yep. It's linear, so we're going to imagine that there's going to be this linearness. Linear. Linear. How do you spell it? I hope it is. Did I spell it right? Okay. So, same thing as the last one. Start with the 2 carbons. And again, I'm hoping we're starting to get the hang of this. From this above here, it's SP, so you're going to write some SP hybridized carbons. It's looking like that. You're going to put your electrons into them. You're going to look at the 2 of them, and you're going to look for opportunities for overlap. So hopefully you should be able to go ahead. Carbon, HE, also SP. You'll notice I didn't label it up all that much. We can see that those are SP. We've got the 2 identical type orbitals. 1, 2, 3, 4. 1, 2, 3, 4. I have to have 1 sigma bond between the 2 carbons. That happens between hybridized orbitals. And the 2 other bonds are pi bonds. I've defined that for you. And you can see here we've got 2 sets of unhybridized p orbitals. We can form a pi bond there and a pi bond there. Pi, pi. So there's our triple bond, the sigma bond and 2 pi bonds. And just to add the H's, just to make life easier, well, we make it easy. I make it easier by putting all H's. If I were to have a fluorine on the end of it, I could have an unhybridized p orbital doing an end-to-end overlap with that hybridized orbital, and it would just be, I'll show you what it would look like on the orbital view. I won't have you write it all out. I want to keep it fairly simple. Okay, so the orbital view. And again, I'm going to cheat just because that's a way to do this, I think. I'm looking for SP. Anybody see an SP? Where's my SP? Right there. So SP, it looks like a p orbital, but I've got 2 different colors there. And I'll take another SP, and I don't really need to overlap it or rotate it. It doesn't matter. They can overlap like that. You know what? I will flip it around just so that the colors look the same. You guys don't need to worry about the colors. So we'll overlap it like that. Great. Excellent. And there we've got our electrons in it. Let's put the hydrogens on there too. So we'll cheat and we'll put the hydrogens on there. So there's one there. There's one there. And it should be kind of all nicely in line. And we'll put some electrons in those things. There's the sigma bond right there. There's the sigma bond right there. And there's the sigma bond right there. I'm going to write a sigma in there. Now the p orbitals. Each electron, or each atom still has 2 p orbitals. One's going to be going up and down, and one's going to be sticking in and out. And I'm going to cheat by just dragging them in there. You guys are going to do your prospective things. And you know what? Sometimes it's easier to see me draw it, but this does look a lot nicer. So I'm going to need a PZ and a PY. So I've got a PY there. We'll put it in there. And I've got a PZ. And I'm going to bring them all in, even though it's going to make the picture fairly complicated, because I do have to get the overlap right. And again, I apologize. I don't know. I did it on the board for you. Normally on the overlap, I would just show that line heading in the back there, because you guys can't do the shading. I don't know how we're doing on this. How's it looking? Yeah, it's getting kind of ugly. It's getting kind of ugly a little bit. I'm not going to make you draw piles of these things. I might make you draw one on a test. But I think it's useful to see what the p orbitals are doing so that when you look at a Lewis diagram, you can imagine that in your mind. All right? So I need to do the same for the next one. So I'm going to have a y in here, and I'm going to have an x in here, or sorry, a z in there. Okay, perfect. It's looking good. So now I've got to do some overlap. Hopefully you can imagine that these two top ones can overlap this way, and the guys in the back can overlap that way. That's going to be a tricky thing to draw. We need to kind of look at our shading perspective. I could probably shade this top one in like this. I could shade this like this. There's nothing wrong with that. I can shade that there. I want to shade the bottom part, the second part of that pi bond, but this one's actually sticking out in front of it a little bit. So I'm going to take some of this yellow, and yellow is going to be hard to see. I'll use blue. And I'll shade the front of this pi bond first. And now that I do have some space, I'm going to shade the bottom of this pi bond down here. But it kind of hides in behind this orbital here. Ooh. Can we see the three-dimensionality maybe? There's overlap in the front. There's overlap at the top and the bottom. Where's my last little bit of overlap in order to finish this picture? Yep. It's in the back. That's going to be a tricky thing to do, which is why I don't make you do this a lot. But it would have to overlap from here over to there. So it's got to overlap in here, and then it's going to hide behind this peachy colored one. And it's going to then come out in behind here somewhere. And it's hard really to see that guy back there. Oh, I don't know if we can even imagine it. Can we imagine it? Yeah, we got good imaginations here. And again, there's a pair of electrons in this guy, and there's a pair of electrons in this guy. And there are 4 regions of overlap. Triple bond is very strong. And to rotate this, it's also very difficult to do, but you know what? You can't even perceive whether you rotate or not. The whole molecule is a line anyway. The whole molecule is linear. So we have 2 pi bonds. Again, I'll just put a pi down here to represent that that's the one pi bond. I'll put a pi in the back there. And the 3D Lewis. The 3D Lewis becomes quite nice because we're simply going to have carbon, carbon. We can put the other 2 bonds, hydrogen, hydrogen. Okay? The purpose of me doing the orbital view is so that when you draw this and you analyze this and you think SP, you imagine, oh, I've got the 2 SP orbitals and I've got this overlap on the front and the back and the front and the back, top and the bottom, and you can imagine that kind of shape. That's what I want you to be able to do, is look at a Lewis diagram and imagine that shape. So let's now just do some random examples here. Let's do an H2CO. Let's do an H2CO. And I'm trying to think, how many examples am I going to do? I'm going to do this one, and then the next one, and then a third one. So I'll do 3 more examples. And I'm hoping we can go a little quicker. Yep, that's excellent. That's all you need. Ben wrote it like this. And we're short one thing. Yep. Yeah, how many on the oxygen? 2 lone pairs. Excellent. So now we need to do an analysis of 2 of the atoms. The hydrogens are easy. We need to analyze this guy, and we need to analyze this guy. And hopefully you can go ahead and do that, keeping in mind we don't count the pi bond, which is the second bond, in this accounting. I hope we got down to there without assistance. They're both 3, which means they're hybridized the same. I need 3 identical orbitals. What type of hybridization? spp, sp2. So the EPA for both of them, in other words, what shape are we thinking? Trig plan, it's going to be a triangular planar. Trig plan. You know what? Let's forget about the energy level diagram. Well, do we need an energy level diagram? Do we need an energy level diagram to visualize this? I don't think so. I don't think so. Because what am I going to have? I'm going to have 2 sp2 hybridized orbitals, which means I need the loops with then the p going up and down, right? Can we make that jump? It means, can I go straight to something like this? I need my sp2, which I know from my picture over there. There it is. So I need an sp2, and I need a second sp2, and I got to rotate it so I can have the sigma bond overlap on that, right there. What else do I need on those hybridized sp2 hybridized carbons? What else needs to be added? What's still there? I need a p orbital on both, sticking up and down. Maybe we do need the energy level diagram. Maybe we need to see that p orbital. But we do, we need it. We need the p orbital, and it's going to be an up and down one, this guy here. I can even go back to this. One of these has to be a sigma. There it is. One of these has to be a pi. Double overlap there. What do I need on my carbon? Yep, 2 hydrogens. I'm going to get lazy here. I'm not even going to grab the circles because I can draw circles pretty easily. There's sigma bonds. I'm not going to put that in. What do I need on the oxygen? What do I need on the oxygen? Christian, what do you got? Yeah, I don't need to put any bonds in there. I just need lone pairs of electrons on the end. You'll notice that thing looks essentially like the H2C CH2. The only difference is we've got a couple of extra electrons in oxygen, which means we don't need to have or hydrogen stuck to it to fill the octet. It's really the same structure. 3D Lewis. We can put it flat on the board again. And really, to do it right, we should put the lone pairs off at that 120-degree angle. We don't put lines there to represent that, but we should have them hanging out there in that fashion. And we should do that. Did we get all the information we wanted there? HCN. Now, when I give you the textbook questions after this example and the last one, the textbook is going to ask you questions, very simple ones like, what's the hybridization of the carbon in these following compounds? Or it might say, what's the shape, right? What's the electron pair? But I go through the entire process with you. Some questions might not ask for the entire process, but I'm giving you the entire analysis of from right the beginning to the end three-dimensional Lewis diagram of these. So it's a little different. Again, hopefully you're going ahead of me. H, C, and I'm hoping you came up with something like that. So in the analysis, I've got one lone pair, one bond pair, two. Here I've got two bond pairs, zero lone pairs, two. Type of hybridization. I only need two of them to be exactly the same. SP, 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 EPA. What are the shapes of these things going to be? Yep. Linear. And we could probably jump straight to the 3D Lewis at this point. And that's where I eventually want you to get. If we've determined that it's linear, then we can, well, actually, I've already drawn it the way it's supposed to be. I've drawn the 3D Lewis diagram because I already know already ahead. H, C, triple bond, N, there it is. And that's ultimately where we want you to be when drawing these things. Okay? What do I want to do? I'm gonna do two more. I want to do one, I want to shake one more thing up. Don't worry about the orbital view. If you started drawing it, that's great. You're going to have two pi bonds. One's going to be up and down, one's going to be in front and back. I'm not changing my mind. I'm going to do two. And I'm making this one up, so this could be trouble. Let's do CH3. Oh, yeah. CH3, COOH. This is the acetic acid molecule. I gave you this again last year as one of the ones near the end. And to get the Lewis diagram was always a little bit of a struggle, so I might need to give you a hand. We're telling you that this is going to have this on it. Then I've got a C. And you're going to find that I can't just string it all together because that C won't be happy, because I'm only going to have two bonds on that C. So I'm going to tell you, I'm going to help you out. OH. And we are going to go from hybridization right to a 3D Lewis diagram. Oh, yeah, it's fun. Because as you can imagine, the energy level diagram is just going to be chaos, because I'm going to have carbons with carbon and then carbon with an oxygen, and then the orbital view is going to even be more chaos, which is exciting. So let's just eventually get to a 3D Lewis. So what we need to do is we need to analyze every one of these guys in the middle. We need to analyze this guy. We need to analyze this guy. We need to analyze this guy. We need to analyze this one. Because they're all going to have their certain shapes depending on what type of hybridization they have. So go ahead and determine lone pairs and bond pairs for each of them and determine their hybridization and their EPA so that we can get an idea on how to draw them three-dimensionally. Oh, I screwed that up. 2 lone pairs on that. Did we get that? First one, I have 4 bond pairs. So what type of hybridization is it? sp3. So what's the shape? Tetrahedral. So that one's going to have a tripod type action. This next carbon is 3 bond pairs, 0 lone pairs. 3, what's its hybridization? sp, that's not an S, that's a 2. sp2, right? So what's its shape? Triangular planar. Don't have it written down there yet, but it's a trig plan. Trig plan. 2 and 2, 4. What's its hybridization? sp3 tetra. That's got to have a tetrahedral shape to it. And what's this guy? sp2, and what's its shape? Trig plan. Okay, that's exciting. I'm going to start with these trigonal planar ones in the middle for no reason. That means 3D Lewis, I've got a carbon, I've got a couple of, or I've got a double bond oxygen, and those are both trigonal planar, which means they're going to go off like that. Trigonal planar, trigonal planar. Connected to this one is a carbon. And what shape do I have to have around this carbon here? Tetrahedral. It's going to be sticking out this way somehow. So I'm going to have my tripod heading out that way. Right? You could draw it just like we normally do if you turn your head sideways a little bit. Imagine that the whole thing is up and down. I'm going to need a bond maybe along the plane here. Then I need one sticking out, and I need one going in behind. And it really didn't matter what order. I could have had it down this way, sticking out and going in behind up that way. Doesn't really matter. Hydrogen, hydrogen, hydrogen. O. What shape is it? Tetrahedral, but 2 of them are lone pairs, which means we really don't have to worry about the lines. I could make this bend up this way, and then my 2 prospective lone pairs, one's coming out and one's going in behind, but you can't really see them, because you can't really see lone pairs. You can just see the nuclei. So there's a 3-dimensional O, right? It's not that exciting. And on the end of it, an H. $15. Yeah, that's a good place to stop. I was going to do one more, but I'll save it as a little review tomorrow. So we'll stop there. Just 1 second here. There is some homework that goes with it. Don't have to write the question down. This is just something just to kind of summarize. You could write the homework down, obviously. But we can answer it. How many sigma bonds and how many pi bonds are there in this particular molecule? By the way, this molecule is called benzene. It's a very special molecule. We'll be looking at benzene and different aspects in the future. How many sigma bonds are in this molecule? What do we got? How many? Was there 12? How many pi bonds are in this molecule? 3? Yeah, I agree. The double bond is a pi bond, so there's 1, 2, 3. All the rest of them are sigma bonds, and so there are 12. All right, and I'm going to stop there.